can have a look at NICE chapter 2.3. The transfer function of a linear system is defined as the ratio of the Laplace transform of the output variable to the Laplace transform of the input variable. So it's a ratio of something of s over something of s. When all initial conditions of the linear system are 0. So that's important. We're not having arbitrary initial conditions, that they're 0. So if you have this differential equation, we know from experience that this is like a spring mass damper system where y is the output and r is the input. This is the forcing term, the input, and this is the result, the equation, the dynamics. So if you drew a block of this, then you'd see that it's r going into it, and this is the plant or differential equation in ODE, and the output is y. Cause effect. You do something with r, and then y changes. The Laplace transform of this ODE, when you set all initial conditions to 0, is given by this. We've done an example of this already. So you get this expression. So to find the transfer function, we need to take the ratio of output over input, which is y over r. And if you do that, you're left with this rational function. This is the transfer function between input r and output y of that system. That is just like writing the differential equation with the assumption that the initial conditions are 0. It's an alternative way of writing a dynamic system. Like it's a transformation of that system in a form that's we're going to see is very useful. So in general, the transfer function is a ratio of polynomials like this, where the order of the numerator is usually less than or equal to the numerator. In most cases, it's less than the denominator order. If you set the denominator to 0, it's the characteristic equation, which is the one you've used in solving differential equations in the time domain. You know, when you have the homogeneous, and you might have seen this instead like this: lambda squared plus 7 lambda plus 3 equals 0 as a characteristic equation. Yeah? I'm just using s instead. But both lambda and s are complex variables. You remember that when lambda, the eigenvalue, could be a complex number? Because you're actually in the complex domain when you're looking at that. So that's the characteristic equation. And then the roots of the characteristic equation are called the poles. That's why I've used it interchangeably before. I'm so used to saying the roots of this equation are the poles of the system, and the roots of the numerator are called the zeros of the system. Zeros because if you set s equal to the 0, the whole thing is 0, and you get no response at all, flat lines. We only really see that when we look at frequency analysis with Peter Hsu, but that's where the name 0 comes from. Poles and zeros. So if we can graphically visualize the poles and zeros, it helps to try to figure out what kind of system we have. So we plot this on the S-plane, or complex plane. You've seen this before in mathematics, where you plot the real axis and the imaginary axis. So that's the real part of that S variable, and this is the imaginary part of the S variable. And if a transfer function looked like this, you would factorize both the numerator and denominator to find the roots, and so the poles and the zeros. You mark the poles as x's, so that it has 3 poles, 0, and this complex conjugate pair. Hey, is that the same one that I used in my example? Yes, it is. So yeah, -1 plus or minus 2j is indeed the solution of that. And it has 1, 0 at 2, right? S equals 2 makes this top line 0, and you on the Argand diagram or pole zero map, you show the zeros as O's, poles as X's. So there, graphically, that's where the poles and zeros are located for the system. And that's enough information for me to actually tell you stuff about that system. If that was a real system that we modeled, a spring mass damper system, I could tell you stuff about what's going on. I could tell you that it's marginally stable, meaning if you gave it certain inputs, it would go unstable, but if you gave it other inputs, it would actually look quite benign. I could tell you that the response would have some oscillation in it, and generally it would be underdamped, so you'd get this kind of ringing, and then it'll die. I can tell you that it's non-minimum phase because of the zero in the right half plane, which means when you perform an action on it, it'll actually move in the opposite direction of that action before going forwards. All of these things I can tell from my experience of looking at pole zero maps, and you will gain some of this experience in this course. Hence the advantage of dealing with the transfer function and knowing the poles and zeros. The transfer function can be represented as any of the blocks in a block diagram. It could be your sensor, it could be your actuator, it could be the controller, it could be but in most cases it's the plant that has the most dynamics in it. So here is my transfer function, G of S. Some people use T of S. You can use anything you want to represent the transfer function, just like you could use any variables to represent the input and output, like U and Y, or R and Y, or R and Z, I don't know. So my transfer function exists inside this block. This is a typical type of question, and if you look at past test questions, you'll see something like this in there. Find the time response of a system y of t with a transfer function given by this to a unit step input. All right, so for this problem, I'm giving it this signal, 0, and then jumps to 1, the unit step. And I'm interested in how this output evolves in time. That's the time response. And a unit step in the Laplace domain is 1 over s, if you look at the tables. Okay, the Laplace transform of this is 1 over s. I want you to plot y of t and find the pole zero map. Let me just start by finding the pole zero map. G of s is equal to 2s plus 1 over s squared plus 5s plus 6. So let me find the poles and zeros of this. Just leave the numerator alone at the moment. 2s plus 1, I factorize the denominator and I get s plus 2, s plus 3. So I have 1, 0 at what? At s equals what? Negative a half, that's right. I could have factorized this, I suppose, and into something like 2 times s plus a half. And I've got two poles at the values -2, -3. So my pole zero map looks like this. Cool. I have to draw straight lines here. There we go. So this is the real part of S. This is the imaginary part of S. I have 1, 0 at -1/2, so 1 right there. That's at negative a half. And I've got two poles at negative, one at negative 2, one at negative 3. So let's see, half, 1, 2, 3. I've got one there and one there. Not very exciting, they're all real numbers. So the transfer function g of s is defined as the ratio y of s over u of s. So we rearrange for y of s. It's just g of s times u of s. G of s is this thing, but what is u of s? U of s is the Laplace transform of our input u of t. And we're told that the input we're giving it is a unit step. The Laplace transform of a unit step is 1 over s. So here we have 2s plus 1 over s plus 2, s plus 3 times 1 over s. And you'll get to find the time response of other input functions, like a unit ramp or a unit parabola, basically any function that we want, because we can convert that into the Laplace domain, as we've been doing. So this part may change. It's a common mistake to not include the input when trying to find the response. People just go with a transfer function and take the inverse Laplace of that. But that's not going to find y of t, it's going to find g of t, whatever that is. What is that? I don't know. It's actually called the impulse response, which is basically what y of t is when u of s is 1. And u of s is 1 when the function in the time domain is a direct delta function. So it's the impulse response, is if you find the inverse Laplace of the transfer function. Okay, so given that, we want to find inverse Laplace. How do we do that? Just like we've been doing, we find the partial fraction expansion, because we can't take the inverse directly. Now the reason I used the symbols y and u here to represent input and output was because they are recognized in the question as being input and output. Otherwise I could have used any symbols to represent those things, but it does say the response y of t, which you'd assume means the output, and then it says input is u of t. Although that was really the step input, step function, I use the same symbol y and u. And then this is the definition of what a transfer function is rearranged. So partial fraction expansion, this is one big rational function with distinct roots of the denominator, because the roots are 0, -2, and -3. So I can just use cover up for all the residues. So here's my partial fraction expansion. And then I use cover up for each one. So for the s part, I cover this part up. I evaluate this at s equals 0, and I get 1 over 6. So that's 1 over 6 over s. For the k2, I cover up the s plus 2 term, and I evaluate the rest at s equals -2. So on the top, I get -4 plus 3 is, sorry, -4 plus 1 is -3 over 1 times -2 is -2. So -3 over -2 is 3 over 2. And K3, cover up s plus 3 and evaluate the rest at s equals -3. So 2 times -3 is -6 plus 1 is -5
over negative 1 times negative 3 is 3. Negative 5 over negative 3, negative 5 over 3 is negative 5 over 3. Yeah? So you got what you guys got? And then the inverse Laplace of that, inverse Laplace of that. Left-hand side of y of s is y of t. Right-hand side, these are nice simple functions you can look up in the table, or just remember. Eventually you're going to remember the simple ones. Like this one is just 1 over 6. This one is 3 over 2 e to the negative 2t, because of the 2, and then this one e to the negative 3t. So this is the time response. This is how the system, or the transfer function, is going to respond in time given an input, a step input in particular. It'll respond differently to a different input, obviously. And you can have a practice at trying to use a different input, find its Laplace transform, resolve this, and see what that looks like. Now I want to plot this, so let's draw up some axes. And let's plot it. Oh, okay. How are we going to plot this thing? Well, I'm looking for distinguishing characteristics of this function in order to plot it quickly. I just want to sketch it. I don't want to like get a table out and start putting point by point. So a distinguishing feature of this is the fact that as t approaches infinity, these two terms disappear because of their negative exponentials, which means we're only left with this one. So this is actually going to be the steady state value, which in control is basically the limit as t approaches infinity of y of t. Definition. So 1 over 6 is where this thing will end up. So it's going to end up somewhere over here at 1 over 6. And then what's it going to do until then? Well, you could evaluate it at 0, and you'd find that in fact it starts at 0. This function is fairly well behaved, and its initial conditions are 0. By definition, the transfer function. And then it does something in between, which I don't care about too much at this point, but it does something like this. You can peek on the next page and see that that's the right answer. When I do it in MATLAB. I can also find this final value, the steady state value, using the final value theorem. Y steady state by final value theorem. Oops, theorem. And the final value theorem is at the bottom of the Laplace transform table, or very close to the bottom, which says that f infinity, which is the same as the limit as t approaches infinity of the function f, is equal to the limit as s approaches 0 of s times the function in the Laplace domain. So instead of doing a limit in the time domain, you could do a limit in the Laplace domain to find the final value or steady state value. So, I mean, this is just another way of writing it. But from the final value theorem, it's S approaches 0 of S times the function in the Laplace domain. Now that's often easier because along the way we may not have found the response in the time domain. Everything might be still in the Laplace domain. So y of S is this thing here. Is it 2s plus 1 over s plus 2 s plus 3 times s. It's the limit of all of this you can, without loss of generality, cancel the s's from the numerator and denominator, and because there's no discontinuity at s equals 0 in what remains, you can just evaluate this thing at s equals 0 and you get 1 over 2 times 3 is 6. And look at that, it matches what we found up here. At least in one of the problems for tomorrow's tutorial, you have to find the steady value. Questions? Yep.
Why S is approaching 0, not infinity?
Because we're in a different domain, and it's just part of the theorem. I don't have a proof of that theorem. But in that other domain, different things happen than what you're used to in the time domain. That's all I can say, I suppose. We're not approaching infinity, we're approaching 0. There are some reasons to do with how S represents a frequency, and that what we're doing is evaluating it when the frequency goes to 0. And when the frequency goes to 0, we call it the DC gain. And if it's electrical kind of system, it means the steady state gain, which is 1 over 6 with this final value. It's the part without the transients. See, all this stuff here, from 0 up until infinity, is what we call transient behavior. And then after that, it's settled. After some time, you don't wait forever. But to some time, you say it's settled, and then that's called the steady state value, or DC offset, 1 over 6.